Okay, let's begin. I heard someone had a question on chapter 4. Huh? 32. What? 32. Well, I don't have the book. What is
But the one where the square of a, b is greater than, assuming a and b are positive reals.
A and B are positive real numbers?
Yeah. And given that the square root of a positive real is always a positive real.
Square root of x is positive if x is positive?
Yeah.
X and R?
And then, or I mean, I guess the square root of x is always positive if it's not 0, but anyway. And then square root of ab is greater than or equal to, or sorry, less than or equal to.
Square root of AB?
Is less than or equal to a plus b over 2.
And also, they're all greater than, both of them are greater than 0.
If AB are greater than 0?
Yeah, that's in the
No.
positive. That's in the positive real.
Inequality, 0.
Oh yeah, 0 is
0 is
less than.
than.
Over here?
Yeah.
Yeah, well, not less than.
Not equal to. Not equal to. Just.
Okay, well, this part we don't really have to prove because it follows directly from that, right? If A and B are positive, then their product is positive, and so we have this is greater than 0. Okay, so that's fine. What about this part? What did you try?
So what I did, I said a plus b. I set a plus b over 2 equals x. Right?
Okay.
And then I said take some number y such that a minus b over 2 equals y.
Okay. Set y such that
Yep.
A minus B over 2 equals y.
Yep. So then a equals x plus y, and b equals x minus y.
So A equals x plus y,
Mm-hmm.
B equals x minus y.
Then if you multiply a b, you get x squared minus y squared.
So AB equals x squared minus y squared.
Since y is a real number because it's composed of real numbers, then y squared is always positive, so x squared minus y squared is always less than x squared. Right? And then plug in, then you already know a plus b over 2 is equal to x.
Okay. Yeah, so
So then you take the square root of those two sides and you have square root of x squared minus y squared is less than the square root.
yeah, this applies here. Right.
Yeah. So then,
Interesting. How did you come up with that?
I was recently working out trying to derive the quadratic equation, and I used that technique
Oh.
to express two numbers as.
So this works. I wouldn't have done it this way, but let's write it down. Let's write this down nice. Method 1. So set x equals a plus b over 2, and y is equal to a minus b over 2.
How do you get that? I don't know. Did you get the y?
Well,
Yeah, he's like, how did you come up with this for y?
So I realized that you can express two numbers a and b as their average plus or minus the distance to the average.
Okay, yeah,
So x is their arithmetic average.
yeah.
So that's the first part, and then y is just half the distance between the two. So that's the distance to the average.
Okay, so you had some sort of geometric intuition coming into this, I guess.
Yeah.
Yeah, but I'll show you how I would have done it, but let's just write this down. So you said x equals this, set y equals this. There's some geometric interpretation to come up with this guy. And then a is equal to x plus y, and b is equal to x minus y, which means that AB is equal to x squared minus y squared. Since y is in R, y squared is greater than or equal to 0. I would have used this fact and then do something, but I'm going to show you.
Yeah, that's what I wrote it down as.
So I'm going to use this fact, but in a different way. So since y is greater than 0, you know that AB equals x squared minus y squared is less than or equal to x squared. And we've actually proven, so AB is less than or equal to x squared, which implies that the radical of AB is less than or equal to x, which is equal to a plus b over 2. Right? We actually proved this. It's one of the first examples I did with real numbers, right? So we know that if x squared is greater than y squared, then x is greater than y, right? So this fact follows from that. Probably how I would have done it was something like, note, let's make sure we're not using this. If x is in R, then x squared greater than or equal to 0. So I know that radical A plus radical B all squared is greater than or equal to 0. So that's A, I want a minus here. A minus 2 radical AB plus B is greater than or equal to 0. Which means that A plus B over 2 is greater than radical AB. So, yeah, this is valid, but I don't think I would have seen that, or maybe not a lot of people would see that. I feel like more people would see this. But that's just my opinion. Right, so either one of these would be fine. I think this would be a more typical approach. Yeah, because I believe your book did examples where it actually did this sort of manipulation, used the perfect squares to expand the formula and get something else. But yeah, so that's probably how I would have done it. But this is fine. This is sort of, yeah. I feel like it's like you said, you would have had to have been working on something else where you sort of were doing this sort of manipulation to actually see it. Like out of the blue, I don't think I would have seen that. Yeah, so. Okay. Yeah, so let's get back to what we were doing in chapter 5. We basically just started off. I think I sort of botched what we were talking about examples, so I thought I'd just rewrite that a little bit more concisely and probably a little more accurately. It's sort of hard to describe because, like I said, there are a lot of variations to this thing, so I can't, it's hard to come up with universal rules all the time. So let me just mention again the use of examples, and then we're going to talk about proof by contradiction. Just to sort of be concise and sort of give you sort of a rule of thumb when we can use it, when we cannot. You can use examples to disprove a universal thing. I put universal in quotes because that's where the vagueness can happen, so I'm going to try to just explain that. And here the example is called a counterexample. You can also use an example to prove an existence thing. So if you claim this thing exists, you just find an example of that thing and say, here it is, it exists, you know. You can not use examples to, first of all, you can't prove a universal thing. And again, universal is sort of used loosely here. Or to disprove an existential one. I guess to sort of expand more on what I mean by universal, for sort of this rule of thumb. If there are too many possibilities, so abilities to reasonably exhaust then you can't use examples. Right, so obviously if we have some sort of thing where we have an infinite number of cases to talk about, so if you want to say something about all odd numbers or all even numbers, then you can't use an example because there's an infinite number of them. You have to give an infinite number of examples to actually prove that by example, which is actually impossible. But universal, I put it in quotes because you can have a claim something like, let A be the set 1, 2, right? Just two elements in the set. For all x in A, blah. Then it's reasonable. If you just have two elements, you could, depending on the claim, you could reasonably go through all possible cases with 1 and 2 and prove it on a case-by-case basis, which you'd say use cases, not really examples, but that's sort of what I mean. In general, what it means is if there are just too many things for you to verify by hand, you can't use an example to prove it. Existential claims are not this way. It's because you just have to find one example to prove an existential claim, which is reasonable to do by hand. Right? So that's just a general rule of thumb, how we deal with examples. So after we did that and we talked about some existential claims, we sort of introduced the proof by contradiction. And basically, it's a principle that says we can actually prove a claim by proving its negation is false, and we can prove its negation is false by proving its negation leads to a contradiction. Its negation implies a contradiction. So now we're going to talk about chapter 5, continue, and I'm going to specifically tell you what a proof by contradiction would look like for an implication, which is a very important kind of claim. So, proof. I'm going to do a bunch of examples, and then move on to prediction of P implies Q. So let's say this is your claim, P implies Q, and we want to prove it by contradiction. The first step is to assume, what do you think we assume? Assume the negation of this. So what's the negation of P implies Q? How do you guys look that do that? P and not Q. Right? So this guy we know is actually the negation of P implies Q. So what you're going to do is you're going to assume the negation is true, and then basically show that the negation leads to a contradiction. Show that this assumption implies some contradiction. And the contradiction can be anywhere. Anywhere in all of math that breaks down because of this assumption is good. Sometimes it'll be very close to home, it'll be right in your proof. If you contradict some previous assumption, that's good enough. But if you break something elsewhere, that's also fine. Right? So it's this contradiction is in the general sense. Once you can prove that this guy implies any false claim, then it means that this guy has to be false, which means that that guy has to be true. And so that's basically how we prove something, a P implies Q statement by contradiction. So let's actually do some examples. It's a sort of silly one to use contradiction on, but I just want you guys to sort of see a comparison. And see, did I say 5 plus 2 if 5n plus 2 is even, then is even. Okay. So if you saw this on a test, how would you actually do it? On a quiz or an exam or a test? I do the contrapositive, right? So, I mean, I'm going to use contradiction here, but just so you know, if I saw something like this, I will use the contrapositive. Okay, so but we're going to do it by contradiction. Do you guys know about Dexter's Laboratory?
Sure.
The cartoon?
Yes.
You guys actually know about that? Yeah, it was one of my favorite cartoons as a kid. So, there was this episode, right? So, you guys know about it. This genius kid with a laboratory under his bedroom. His parents don't know about it. He's super genius. He has this sister named Dee Dee who's a ballerina, and she's blonde and she's an idiot, and she breaks everything. Okay, so he's a genius scientist, right? Mad scientist, but he's not good at, obviously, artsy things. So he has this French exam one day, right? And he's like, damn, I gotta study for this French exam. So he gets one of those tapes that's supposed to teach you French in your sleep, right? So he starts to press the tape. You guys, have you seen that episode?
It's been a while.
Yeah,
Probably
so
10 years.
so he presses play on the episode, but the tape gets stuck and it starts to loop. So it's like, okay, today we're going to learn how to say cheese omelette. Omelette du fromage. Omelette du fromage. Omelette du fromage. Omelette du fromage. So this is playing over and over while he's sleeping. So he wakes up the next morning and the only thing he can say is omelette du fromage. Like, only cry, omelette du fromage. That's the only thing he knows. Omelette du fromage, omelette du fromage. He can only say that. So he goes to the class, you know, and his test is like, I condensed the entire semester into one question. What is cheese omelette? Omelette du fromage? Okay, omelette du fromage. So he goes to the whole episode only saying omelette du fromage, and somehow he becomes world famous and rich because of this and blah, blah, blah. Okay, so, crazy, right? So let's say you want to study for this exam, you put in the tape, and it gets stuck on proof by contradiction. And you're like, you only know proof by contradiction now. So that's why you wouldn't do this via contrapositive. That's the only conceivable reason I can think of. Right, you go on the test and you forget everything except proof by contradiction.
So just write omelette.
Omelette du fromage, you know. Okay, so if we're doing this by contradiction, what would we assume? So we'd say assume to the contrary that 5n plus 2 is even, and or they usually use the word but n is odd. Then what would you be able to say? N is 2k plus 1 for k is leading, which means that 5n plus 2 is going to be 5 times 2k plus 1 plus 2, which is going to be 2 times 5k. This will be 5 plus 2, which is 7, which is odd. And then you're like, oh, but we assumed this was even, and now we get that it's odd, right? This contradicts our original assumption.
Which is really
Isn't that like a contrapositive assumption?
well, it is a contrapositive, but the form of it.
And for shorthand, I do this, and a few other people do this. They like write up like lightning strikes instead of contradiction. Okay, right? So it's very close to a contrapositive. The thing with contrapositive is you assume not Q, and the thing you're looking for to break is P, right? Which is the original assumption. So whenever your P actually breaks, it will look very similar to a contrapositive. But a contradiction doesn't have to break the P, it can break anything, right?
Okay.
So for this, it would be very similar to a contrapositive, but, you know, omelette du fromage. Right? We are going to do things where it breaks crazy things, and you'll see them in your homework. There are lots of problems in the book. So that's what a proof by contradiction would look like, and you can do a proof by contrapositive and see how it looks. It will be very similar. Proof by contrapositive would have this section in it, which is not key. Okay, so for this example, we're going to make an assumption, which you're going to prove in your homework, so I'm not going to prove it. Assume that the product of an irrational number and a rational number is irrational, right? So if you take an irrational number and multiply it by a non-zero rational number, and a non-zero, right? Because obviously you multiply by 0, you get 0, you get it's irrational, right? So if you multiply an irrational by a non-zero rational, the result will be irrational. It's actually a homework problem. You're going to prove that. So now prove. So this I'm saying you can assume it as a lemma, right? This is your lemma. Prove that there is no smallest positive irrational number. So how would you do this? Right. So we're going to do contradiction, proof. That there is a smallest. Okay. How do you proceed? Find a smaller one, right, which would contradict this. Okay, so what do we say? How do you find a smaller one?
We can divide it by
Yeah.
Right. So call it R. Then R over 2 is actually less than R because it's positive, right? And so I just take R and I multiply it by a half. And R over 2 is still greater than 0. If I divide a positive number by 2, it's still positive. Since R over 2 is actually irrational, it is smaller than R. Contradiction. So that's another kind of proof you can do by contradiction. So to prove there's no smallest positive rational number, just assume there is a smallest one, and if you find a smaller one, you've contradicted that assumption. So that's a proof by contradiction. A very similar proof you can use to prove that there is no smallest rational number. It would look pretty much exactly the same as this proof. There is a smallest positive integer, so that proof would not work, obviously. But let's do another one. An odd number cannot be written as the sum of 3 integers an even number of which are odd. So the claim is you cannot write an odd number in this fashion. You can't write it as a sum of three integers where an even number of them are odd. Okay, how do we prove it? Assume for the sake of contradiction that we can express I don't think I get it.
Do we have to simply state that it's for the sake of contradiction, or writing it?
No. Really fancy. That we can express an odd number n as n equals a plus b plus c, where none or two of a plus a, b, c are odd. Okay. Then what? Cases, right? So case 1, none of them are odd, right? This means that a equals 2k, b equals 2l, c equals 2n, for k, l, n, and c, which means that n would be 2 times k plus l plus n, which is even, and that produces a contradiction because we assumed it was odd in case 2. How do you write down case 2?
So A equals 2k plus 1, B equals 2l plus 1, and C equals 2n for k, l, or l to c.
We need it without loss of generality. Right? Because it could be these two are the odd ones. So it doesn't matter who are the odd ones, is what we're saying. The proof would look very similar. So the loss of generality, assume A and B are the odd ones and C is the even one. Then n would be equal to 2 times k plus l plus n plus 1, which is even. And again, we have a contradiction. For we assumed it was odd. So, yes?
When we're going about proving contradiction,
Yeah.
I'm wondering, for example, this last problem that we did, if we went with, assume we have an odd number that the sum of 3 integers such that it has to be 2, not 3 or 5. So we write it like in case 2, but then we arrive at that contradiction because we assume it was odd and we just said that it's even. Can we just stop there? Just do that cover instead of having to say this part, 1 or 2 of these are odd. I kind of feel like that's like extra thing to do.
No, the thing is, 0 is an even number. So we have to cover the case where 0 are odd. Yeah. So if you're talking about 3 things, the even numbers would be 0 or 2. Yeah. So that's why I have to do the case 1. Okay. Here's another one. The sum of a rational and irrational What do you think it is?
Irrational.
It's irrational. Proof. How do you prove it?
Assume that it is rational.
Suppose R is an irrational number, and let's do Q is an irrational number, and suppose R plus Q is equal to A over B, such that AB is an integer with B non-zero. So I want to prove that the sum is irrational, so I assume the contrary, that it's actually irrational. What would I be able to say?
So subtract Q from both sides.
Alright, so R would be A over B minus Q.
And since you're just using addition, subtraction, and multiplication, or since A minus BQ is an integer.
Right, this is an integer, and B is a non-zero integer, so we get this, which is a contradiction, because I assumed R was an irrational.
We technically have to represent Q as some like M over N. So Q is technically an integer. So Q is just a rational number, right? Not an integer.
Right, yeah. We would have to, yeah, it's not an integer, but we could express it that way, ultimately. For a problem like this, well, I wouldn't ask something this easy on a test, but I would expect you to recognize this. So technically you could do something like, oh, write Q as N over N, right? And then you can read, so these guys are all integers now, and then you can just write that as a fraction. So that would be NA minus BN over NB. And then you'll make the note that n is non-zero, therefore bn is non-zero. And so this is a non-zero integer, and that's an integer. And then you can do that. Okay, here's one a little more challenging, not super challenging probably. But those are just to get you used to the idea of using contradiction. They weren't meant to be difficult. So the idea is you assume the opposite of what you want and show that, that leads to something breaking. So here's another one. Prove that the sum of the squares of two odd integers is not a square. Or to be specific, a square integer, right? So it's not the square of some integer. In other words, a squared plus b squared equals c squared will not hold if a and b are odd.
So assume that it is a square integer and A and B are odd.
So assume that, what do you want to call them? A and assume that a squared plus b squared equals n squared, where a is equal to 2k plus 1 and b is equal to 2l plus 1 for k, l integers. Right, so I have two odd integers that when I add their squares, I get the square of some other integer. Why is this a problem?
Just do the math.
Well, this one we can use that that other proof where it was, if, the square of a number is even, then the number is even. Is that right? When we get to the part where after we substituted 2k plus 1 part.
Okay, so you squared an odd number, so you get an odd number. You square this, you get an odd number. You add them, you get an even number. Why cannot n squared be even? It's possible for a square to be even. 16 is a square, it's even. Right, that wouldn't be a contradiction. So let's actually just plug these guys in and see what we find. So if I take 2k plus 1 squared plus 2l plus 1 squared, that's actually equal to 4k squared plus 4k plus 1 plus 4l squared plus 4l plus 1. Equal, I don't know, there's a common 4. So that n squared is actually equal to 4 times k squared plus k plus l squared plus l plus 2. What's the contradiction?
But arithmetic represents the number with the remind of, if it's divisible by 4, it will have the remind of 2.
That is correct. We can notice that this is actually equivalent to 2 mod 4. Why is that a problem?
Because square root of 2 is not an integer.
What? Square root of 2 is not an integer? Yeah, but this is a mod thing. How do we know that that translates to?
Be so n squared minus g squared plus k plus l squared plus l blah 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 equals 4 times some number.
So you want to say that n squared minus 2?
So here, so take a 2 out of everything, right? So in order for n squared to be even, n squared has to be, then n has to be even. So n has to be divisible, n has to be 2 times something times 2 times that same something. So it's going to be like 4x squared, right? So the right hand side also will have to be divisible by 4 evenly. Like with no mod. With no remainder.
Right, so, yeah, so if n, so you can use the theorem that we've done, right? So you can use that as a lemma, that if you know the square of an integer is odd, if an integer is odd, then its square is odd. So you know that this must be even, so you know that n squared must be even. Using that same lemma, you know that n has to be even, which means n has to be 2 times some integer, in which case when you square it, it'll be 0 mod 4, right? So that's one way to do it. So, using as lemma, x squared is even if and only if x is even, we can show n is even, i.e. n is equal to 2p for p in z, which would imply that n squared must be 4p squared, which is equivalent to 0 mod 4. And so, therefore, you can use a contradiction. That was one way. There's another important fact that I would have probably used. Alternatively, that will give you the answer right away. Alternatively, we may use as lemma if x is an integer, then x squared is equivalent to 0 mod 4, or x squared is equivalent to 1 mod 4. In other words, a square will always be equivalent to either 0 or 1 mod 4. So immediately when you get here, that's 2 mod 4, you could have said, oh, that's a contradiction. Right? This is actually a pretty well-known thing. Especially if you study number theory, you'd use this fact all the time. Right? So when you get to here, oh, that's 2 mod 4, that's actually off. So you could actually use that as a lemma, or use this as a lemma. You have to apply it twice, and you can get to the answer that way. By the way, how do you prove this lemma? How do you prove that the square of any integer is either 0 mod 4 or 1 mod 4?
Two by cases where x is either odd or even.
Right, we have two cases. Case 1, x equals to n for n an integer, then x squared would be 4n squared, which is equivalent to 0 mod 4. For case 2, x is an odd integer, 2n plus 1 for n in z. Then we have x squared would be 4n squared plus 4n plus 1, which is equal to 4 times n squared plus n plus 1, which is equivalent to 1 mod 4. So a square has to be either 0 or 1 mod 4, so when you get to this and you're like, that's 2 mod 4, there's no way this side is a square. So here you can see we have a proof by contradiction where it breaks some other well-known theorem, right? We never made any assumption to do with this in the beginning, like this wasn't even there. But if you come here and you're like, oh, you knew this theorem somewhere else, you know, you realize, oh, that's a contradiction, right? Because I know this fact, there's no way this can be true. So it doesn't have to break something that you're currently dealing with. It could break something completely different, like some other well-known theorem, right? So that's why I gave you this example. So it means that with a proof by contradiction, you really have to think broad, because you can break something like outside of the scope that you're currently dealing with, and that's fine. Once it breaks anything, that's good enough to get a contradiction. So, just a couple more proofs by contradiction, more for historical reasons actually. So your book does one of them, and I'm going to do another one. These are a couple proofs where if you tell anyone who did a proof class, they'll say, oh, so you know these proofs. You know, it's just something you're supposed to know. Square root of 2 is irrational. That is the claim. Proof. Right? There are actually tons of ways to prove that square root of 2 is irrational, but this proof happens to be a favorite of many people. It's considered elegant by many people. And it's also a proof that you'll see in a lot of books that talk about proofs. This will be one of their examples, and this is actually an example in your book, and I will give you another example of a famous proof by contradiction later. So a very famous way to prove this is by contradiction, and so it goes something like this. Assume to the contrary. That square root of 2 is rational. So we may write square root of 2 is equal to a over b, where a, b are integers, b non-zero, and Right, so we can write it as a fraction and we can reduce it and that's fine. This would mean then that you can square this guy, which would mean that a squared is actually equal to 2b squared. Right? What can we say here?
That's 2 not 4.
It's
Since A and B are odd, if it's in those terms.
A and B are odd? No, you cannot say A and B are odd. In fact, we know A has to be even. Right? A squared is 2 times an integer. This means that A squared is even, which means that A itself is even. That's a fact we proved. So, A equals 2, what's a letter I haven't used? N. Or N. Then, if I have A squared is equal to 2B squared, this would mean that 4n squared is equal to 2b squared, which would mean that 2n squared is equal to b squared, which would mean that b squared is even, which means that b is even. So b is equal to 2n for n instead. Then radical 2 would be equal to a over b. What's the contradiction here?
A and B are both even, or are both divisible by 2.
A and b are both divisible by 2. So a is actually 2n, b is actually 2m. So it means the contradiction is we assume they were in lowest terms, so they cannot be reduced, but it ends up we could reduce them. This contradicts the assumption A over B was in lowest terms. It's considered a very elegant thing. It's like, oh, how do you know, it wouldn't probably be something that you would look for a contradiction in. The fact that you can, if you assume radical 2 is rational, it means you can keep reducing any fraction by 2 forever, essentially, right? Because then if you make this assumption, okay, I made a mistake, radical 2 is actually m over n, then you can go through this whole process again and reduce it again. Okay, my mistake, it's actually p over q. You can go through this whole process again, oh, my mistake, it's actually, and you can do this forever. You'll never be able to reduce a fraction, right, if radical 2 is actually irrational, right? So it has to be irrational. So that's a very famous proof. It's one you should know by heart. Anyone would expect you to know that by heart if you went through a proof course. So just for historical reasons, I have to write that down. Another proof that you probably expected to know by heart is Euclid's proof that there is an infinite number of primes. So that's a claim. And everyone knows what a prime number is, right? So a prime number is just a number greater than 1, right? 1 is not considered prime, where its only positive divisors are 1 in itself, right? So it cannot be broken down into a product of integers other than 1 times itself, right? So that's called a prime number, and Euclid figured out millennia ago that there are actually an infinite number of such numbers, right? So the proof goes something like this. It's one of the oldest ever recorded proofs by contradiction. That's why it's one of the things you have to know. Assume to the contrary. There are a finite number of primes. Say, let's actually number them, P1, P2, all the way up to Pn. Does anyone actually know this proof? What's the next step? You consider a certain number.
So just multiply P1 through Pn and then add 1.
Right, you multiply all these guys. P1 times P2 times P3, and you times all of these guys. And then you just put a plus 1 to it. Right? So he says, assume there's a finite number of primes, and look at this number that I just created. It's clearly another integer, right? Note, this is not divisible by any of the primes. P1 through Pn, right? Because if you divide it by any one of these guys, you're going to get an integer here plus 1 over that P, right? Right? So let me just fill that in. If we divide by some Pi, we get P1, P2, Pi minus 1, Pi plus 1, Pn plus 1 over Pi, right? And this guy here is not going to be an integer, right? Because your p's are 2 or bigger, right? So it's going to be an integer plus a half, which is not going to be another integer, right? So that's actually, so we know it's not divisible by any of these guys. Therefore, it's not divisible by any other prime number, so it must only be divisible by 1 in itself. Therefore, let me actually just call it n. Therefore, n is a new prime. Right? So basically, if you assume there's a finite number of primes, you'll always be able to find another one. Right? For any finite list of primes, this guy will always be a new prime, because none of these guys will be able to divide into it. So he has to be a prime himself. Right? So every time you assume there's a finite list, there's always another one. And this is a contradiction. It means you cannot have a finite list. And so that's a very famous proof of the infinitude of primes, it's called. By Euclid, one of the first to ever write rigorous mathematical proof texts. So those I basically have to tell you for historical significance, because you're supposed to know them. Okay, so that's basically all I wanted to do with proof by contradiction. I think those examples will sort of give you an idea of how it works. A lot of the times the contradiction comes in what you actually assumed, but it is possible that it breaks some completely new theorem as opposed to the third to last, like in the third to last example I gave. So that's just another proof technique under your belt. And that does it for chapter 5. And we are going to chapter 6, where we're going to learn yet another proof technique. Will I have time to do examples? I don't know, because I actually wanted to prove something else about the technique before. A very common technique, mathematical induction. To talk about this, I have to talk about a few other things. Let's look at some definitions here. Like A be a subset of R, it's non-zero, it's non-empty. Then is called the least element or minimum element or something similar. If a is actually less than or equal to x for all x in A. Right, so if you have a number that's less than or equal to everything in your set, you call that number the least element. What do I want to say? It's obvious that not all sets have least elements, so it should be obvious. At least according to the operation less than or equal to. So there's this weird theorem out there that says we can order anything to have a least element, which is really crazy, but no one can figure out how to do it with everything actually. So for example, R, Z, the open interval 0 to 2, D plus R plus have no least element. Right? There's no number in any of these sets that is smaller than or equal to every other number in the set. Right? So this is sort of saying there's no smallest positive rational, there's no smallest positive real number. Right? Another example, if you have z plus, or starting at 0, or n, or the closed interval 0, 2, have least elements. In fact, again, did your book prove this? Probably did. I think your book either proved it or I gave it as a homework. Any finite set of real numbers has a least element. Right? And this is according to this operation. Right? So that's just some examples and non-examples. Right? So the least element here is actually 0, right? The least element in n is 1, the least element here is 0. What else did I want to tell you about? I think what ordering? Yes. So another definition. A subset of R, A non-empty, is called well ordered if every non-empty subset of A has a least element. Example 1, 2, 3. That set is well ordered. While another example, again, if we take that closed interval, this is not well ordered. Why is this not well ordered? It has a least element.
Yeah, because subset of the intervals are
Right. The open interval 0 to 2 is actually a subset of this interval, and this has no least element, right? So you're not just looking at the set itself, you're looking at every possible subset of that set that's non-empty. Every subset has to have a least element. If you have a set where every subset has a least element, that set is called well ordered. Right? That's just a definition. And now we're going to talk about the well ordering principle, which for now we'll take it as an axiom because we actually haven't covered the math sufficient to actually prove it. So for now we'll actually take it as an axiom. It's called the well ordering principle. It's not a huge principle, it just simply states this: n is well ordered. The set of natural numbers is well ordered. Any subset, any non-empty subset of n that you take, it will have a least element. N itself has a least element, and any non-empty subset of n will also have a least element. And that's it. Okay, so let me first, I'm going to abbreviate this walk. And now we're going to talk about the principle of mathematical induction. So I'm going to tell you about the proof technique of induction. It's usually regarded as a principle of how we can prove things, and I might abbreviate that N on mathematical induction. So it says, for every n that's a natural number, let Pn be a statement. So we have a statement that depends on n, right? If 1, P of 1 is true, and 2, P of k implies pk plus 1 for k in n. Right? Meaning, if we know that pk is true, then pk plus 1 is true. Then we know that P of n is true for every n. This is called the principle of mathematical induction, and it actually provides a method of proof. Right? So if you have some statement that depends on natural numbers, and you can prove that it's true for one, and you can prove that whenever it's true for some guy, it's true for the next guy, you in fact can prove that it's true for everybody. Right? So it's like a domino effect. Once it works for 1, it'll work for 2. Once it works for 2, it'll work for 3. Once it works for 3, it'll work for 4. Once it works for 4, it'll work for 5. And it goes on, and everyone just gets knocked down like dominoes. Right? This is called the principle of mathematical induction. Now, are we going to have enough time? I think we will. So I thought it would be fun, before I do like examples where we actually use mathematical induction, I thought it would be fun for us to sort of prove a theorem about it. Your book does half of the theorem. I was thinking of doing the other half. I think it'll be nice for you guys to see a proof like this. I won't be doing proofs like this very often, but here's the claim. The well-ordering principle is actually equivalent to the mathematical induction principle. i.e., these guys sort of imply each other. This is the claim. And we're actually going to prove it. Your book does one direction. Which direction does your book do? I think it does go with what implies MI. So let's start there. It's probably the easier one. Let's prove that that is true. And then we'll go the other way. So it actually proved this by contradiction, which is really nice because we just learned about contradiction. So assume to the contrary 1 and 2 hold, right? Meaning this statement 1 and 2 hold, but Pn is not true for all n. Right? That's how you'd actually start the proof. Did anyone actually read up to chapter 6? Do we actually know, have an idea of where this is going to go? Alright, let me start it off and see if you guys can sort of pick up. We create another set. Let C be the set of all natural numbers such that it's false. Right? So I claim it's not true for all n, which means take all the guys where it's not true, and take all the numbers for which it's not true, and throw those in a set, right? So I made a subset of the natural numbers containing all the integers for which P of n is false, right? Now what can we say?
The theorem must be true that it's going to be bigger than 2.
What's going to be bigger than 2?
Well, since Pn must be false, P of 1 is true, so n must be bigger than 2, bigger or equal than 2.
There's something we need before that, which is sort of why we want to use this assumption. We'll sort of use it here. Use what?
We're going to use the least element.
We're going to want to know the least element here, right? This is a set of natural numbers, a subset of the naturals, which I'm assuming is non-empty because I'm saying it's not true for everyone, which means that the set of numbers where it's not true has numbers in it, right? So, since C is not empty, C has a least element by the well-ordering principle. Call it, what do we want to call it? C? Little c, or little n maybe, n for minimum. Then, since P of 1 is true, right, because we are making the assumption that it is, n must be greater than or equal to 2, which would mean that n minus 1 is actually still a natural number. So if it's at least 2, I can subtract 1 and that'd still be a natural number. Now what can we say?
Well, since by the second one, we can say that 2 is, but has to be greater than 2, and so forth.
Huh?
Well, by that, since we're assuming pk implies pk plus 1, then we have p of 1, so p of 1 plus 1. So therefore, m has to be greater than 2. Has to be greater than or equal to 3.
Yeah, but then if you do that, you're going to say, well, then it has to be greater than or equal to 4, and then it has to be greater than or equal to 5.
And so,
And that's sort of like induction itself. That's why. So it's sort of not the optimal way to do it. I focus on this guy. What can you say about n minus 1?
Why are you assuming that n has to be greater than for this issue?
Because I know it works for 1. Which means 1 will not be in this set. Right? Because this is just a set of numbers where it doesn't work. I'm assuming it works for 1. So 1 cannot be here. So the smallest element here must be at least 2. Which means if I take the smallest element and subtract 1, it's still going to be a natural number. It will still be positive, a positive integer. So here, n minus 1 is a positive integer. And n minus 1 is actually smaller than n. So what can I say about that?
There is no least
Say there's no least element. What can I say about n minus 1?
It's greater than or equal to 1.
Yeah. Something that would help me.
It would be the largest integer,
Is it in C? It's not in C. Right? Because m is the smallest guy in C. n minus 1 is smaller than m, so therefore it's not in C. If this is a natural number that's not in C, what does that mean?
that means
C is what set? It's the set of all natural numbers for which P of n is false. n minus 1 is not in C.
so it's true.
That's true.
P of n minus 1 must be true.
And then wait a second.
But then, by statement 2, P of n minus 1 plus 1 equals P of n must also be true. Right? Because P of n is false. P of n is actually in the set C, where we assumed this statement is false. Right? But now I'm getting it must be true. So that's a contradiction. Yeah, you got a question?
So, well, does that technically prove it though, or do we have to actually say that that means that C has no least integer and therefore it is not?
No, this proves the whole thing, right? So I assume to the contrary that there is some n for which P of n is not true, in which case I would have to assume that P of n is false, but then I mean here it's true.
But can that mean it's not? It doesn't, like, don't you have to combine that with the well-ordered principle to say that, because that just proves that there's no least
Element in C?
element, and then
You could go there as well. I don't think it's necessary to go there. It's clear, I think it's clear that our assumption means that P of n is false, but here we just showed it's true. You can say that. You could bring it back to the well-ordered principle if you want, but that would be more writing. So, I probably would.
where do you use the well-ordered principles in that one?
What if we wanted to go the other way? Assume that we know mathematical induction actually works. How can we end up with the well-ordered principle that every subset of natural numbers must have a least element? We'd use a similar technique, right? Let's make a set. Let A be a subset of n. That's not empty. Okay. And let's actually create another set C. Let C be, now let's make C an appropriate set. What do you think you want C to measure?
All elements such that P of n is true. Or all elements
And in n such that. Now we're assuming mathematical induction holds. There's no reason to go there. What we want to prove is that n has a least element. So how about we let C be the set of all natural numbers such that n is less than or equal to A for all elements in A. So I'm letting this be least of all the guys in A, right? So let's make that set. And what are we going to do with that? We have 10 minutes. I think we can get through in 10 minutes. It's not that long. What can we say about the number 1? Is 1 in C? It has to be in C, right? So note that 1 is in C, right? Because 1 is, of course, less or equal to every natural number. So I know C is not in D. And here's sort of where it sort of gets tricky, which is where we actually use mathematical induction. Also, there must be some C in C such that C plus 1 is not in C. And why would that be a problem?
Second part of the mathematical induction.
I'm saying there has to be some integer in C such that when I add 1 to that integer, I get something that's not in C. Why not? And remember, we have induction, and we know that 1 is in C.
Second. So
Otherwise, C would actually have to be n, right? Because for every element in C, if I add 1 to it, it's also in C, I would literally get all of n, right? Because 1 is in C, then it means 1 plus 1 has to be there. And then 2 plus 1 has to be there. And 3 plus 1 has to be there. And so on and so forth. C would end up being all of n, which would actually imply that your A would have to be the empty set, right? Because you can't have all of n being less or equal to everything in n, right? There can be nothing there to worry about, right? So I know that this must be true. Any ideas where to go from here?
I'm confused about A.
A is just a non-empty subset.
I mean, like the lowercase a. I mean, well, I guess really I'm confused about C. So is C like the union of a bunch of sets such that n is like a bunch of subsets?
No, C is just the set of all elements that are less than or equal to everything in A. So for example, let's say that A is the set 5, 9, 15. Then C would actually be the set 1, 2, 3, 4. And 5, less than or equal to. So that's my example, right? So it's less than or equal to everyone in A, right? I create a set that does that, right? And if every time an element is in C, I add 1 to it, it's also in C, I end up getting C be everything.
Yeah.
Which means that A doesn't even make sense in the first place.
Yeah.
Okay, so
So if there is always some next or some, so if there is some C plus 1 that,
yeah, which I know is not in C.
which is not in C, then C plus 1 has to be the least element of A, or no, C has to be the least element of A.
That is where we're going to go, yes. Yeah, but you have to, yeah, you have to make an argument for that, but that's the gist of it. How are you going to prove that C has to be the least element of A?
So that, yeah.
Right, just as you saw here when I did that C, you saw the 5 in C was actually the least element of A. The biggest element of C is the least element of A, is basically what you want to say. How would you actually argue that? Give me an argument.
C plus 1 is greater than n. No. It's C plus 1.
So,
Well,
hmm?
because we started there, and 1 is a member of C. So, don't you know that's 1? We need to get from, we can do a K because we're assuming that's true.
Well, we need the 1 to apply the induction. That's why I made this note, so that I get this guy is not in C, and I want to use that fact. The 1 actually helps us imply induction, and this is what I said here. Otherwise, C would be n, and this would happen by mathematical induction, which uses the fact that 1 is in C.
So if we,
But yeah, you're almost there. I just need.
so we suppose that there is some least bound. Or no, that's begging the question.
So then is C plus 1 smaller than?
So C plus 1 has to be the greatest. C plus 1 has to be the upper bound.
Okay, so we can argue that C plus 1 is the least element in A.
No, C is going to be the least element in A. Which you could have seen from my example, but we have to get there. How do we get there? We're actually using the C plus 1.
So if n is less than or equal to C, which is less than or equal to A, or which is less than or equal to C plus 1, which is less than.
C plus 1 goes down. And then, we did the other last one.
Well, just contradict this, right? So then there must be, I use another letter, let's say y,
For some.
y in A, such that, what happened? If this is not in C,
Then what?
then y would have to be less than C plus 1, right? Because I'm assuming everyone in C is less than or equal to everyone in A, so for C plus 1, the opposite must be true. There must be an element in A where it's actually less than the C plus 1. But what would that mean?
Y was the least element of A.
It actually means that y is less than or equal to C,
Yep.
right? But C is less or equal to y by definition of C, by definition of the big set. So that y is actually equal to C. And therefore, which means we have a y that's in A such that y is less than or equal to A for all A in A, since my y is actually equal to C, which is in big C, and that's the definition of C. This means y is the least element. Well, it's actually equal to C. It's the least element. So that is difficult, right?
Yeah.
That was tough, and it's supposed to be tough. But when you go on to higher math classes, your proofs are going to look a lot more like this. You're going to be like, okay, let's make this set to measure these things, and let's do this, and it's sort of going to be like, where is all this coming from? But that's sort of where you're going. So right now we're playing around, oh, this is odd and this is odd, but that's really not where it comes from. You prove really important things like this. We're using this to prove things. How do we know it works? Well, we'd have to prove it somehow, right? That this thing works and we can be confident in it. And then you end up having like these meta proofs, you know, where you prove the things you're using to prove other things. And that's actually a very important discussion. So it's just something I thought it would be good for you guys to see. Like in higher math classes, you'll see a lot more things like this. And we'll end there. We'll do more examples of mathematical induction next time. Okay.